continuing that conversation of continuity. So we've talked about this a couple of times now. So finding that a function is continuous at a point, you need to prove that that point f of c is defined, that the limit as x approaches c exists, and we can prove that limit by showing that it approaches from the right and the left the same value, and then that the limit value and the point value are the same. Okay, so let's look at some more practice problems. So number 7 is f of x equals 3x squared plus 10 continuous at x equals 5. So let's do step 1. Plug it in. So f of 5 is equal to 3 times 5 squared plus 10. So that's 3 times 25 plus 10, which equals 85. So step 1, good. Step 2, we want to show that the limit as x approaches 5 from the left is equal to the limit as x approaches 5 to the right. Okay, so we already talked about this before. Do I have anything weird going on at 5? No, so I can plug in 5 exactly. So 3 times 5 squared plus 10, which I already know is equal to 85. And 3 times 5 squared plus 10, which equals 85. 85 and 85 are equal to each other, so the limit as x approaches 5 is equal to 85. So step 2. Good. Step 3, we want to show that they are equal to each other. Okay, so all I do is I take those values, f of 5 equals 85, which equals the limit as x approaches 5 of f of x. Therefore, f of x is continuous at x equals 5. Nice and easy. Okay, so those are those 3 steps. Let's look at one that's maybe a little bit more difficult, which is really what you're probably typically going to see in calculus, which is a piecewise function, some sort of rational function, something where you're like, well, maybe it is discontinuous, because really looking at that function, you probably knew it was continuous before we started. Okay, so wait, is f of x equals x when x is less than 1, 2 when x is equal to 1, or 2x minus 1 when x is greater than 1, continuous at x equals 1? Okay, so let's find out. So first and foremost, we need to do step 1. I want to know what f of 1 is equal to. Well, because it's piecewise, I have to look at which function includes 1 in the domain. So not this one, yes, and then not that one. So when I plug in 1, what function do I use? Well, it's just equal to 2, because that's the whole function. Okay, so f of 1 is equal to 2. Let's continue on. So second step, I want to show that the limit as x approaches 1 from the left, and that the limit as x approaches 1 from the right are equal to each other. So as x approaches 1 from the left, so those are going to be values less than 1. So which one is that? That's this function here. So that's going to be equal to 1. So notice I'm still plugging that x value in, because I can plug a number into this function. I can plug that actual number in, but I'm using the function that represents the values as x approaches from the left. Okay, so that would just be equal to 1. So the limit as x approaches 1 from the right, that's going to be our values greater than 1, because it's positive numbers approaching from the right. Okay, so that would be 2 times 1 minus 1. 2 minus 1, which equals 1. Well, those are equal to each other. So our overall limit as x approaches 1, would be equal to 1. Okay, so our limit exists. Now you might have already seen it, what our issue is going to be, but let's do step 3 anyway. So step 3, f of 1 does not equal the limit as x approaches 1 of f of x. Okay, because 2 and 1 not equal to each other. So what's our conclusion about is f of x continuous at x equals 1? We would say, therefore, f of x is discontinuous at x equals 1. Okay, I'm not saying it's discontinuous everywhere. I'm just saying it's discontinuous at x equals 1. Okay, so that would be a situation where we do our 3 steps and we don't get that conclusion that it's continuous. Okay, now don't think this just means all piecewise functions are discontinuous and all nice normal functions are continuous. You can have a piecewise function that's continuous. Okay, you just need to go through your 3 steps every time.